All right. Um. So first, thought about something yesterday. So I have this I'm on this Intel NUC right now. It's like a mini PC, but one of the things it has is um, it has two Thunderbolt ports, and I do have an external GPU enclosure. And I actually have one of these guys on my desk right now, which wasn't my desktop, but um, I had to take it out because my desktop broke. So Um, yeah, I was thinking about maybe putting this into the GPU enclosure, which is hooked with Thunderbolt, and putting it into my NUC so that I can run an LLM. And instead of like having, yesterday's situation where I couldn't figure out what this actually meant here, this, where is it? Client ADVR. I could have like asked the LLM for more information instead of like pretty much causing confusion on video. I don't know. It's a good thought. I mean, this thing has like 8 GB of VRAM, so it should be able to hold like Llama 3.2. So maybe I'll explore doing that. Yeah, I'll explore doing that, and so this way, going forward, when we start to work on harder problems, um, it'll just go smoother when I have a question. Since I'm doing this alone, I'm not even doing this live. I'm just like pre-recording all of these. Don't really have someone to really ask to clarify these questions, unless you want to watch me do 10 minutes of internet surfing, searching for an answer, which I don't think anybody would really want to watch that. So, uh, yeah, let's explore doing that, and maybe I'll make a video about that too. So, um, yeah, how to set up a local AI and just use it to ask the right questions so that you can get the right answers. All right, let's continue. Um, so we last left off here. Sometimes the server doesn't start properly. If I start the server and then run the client one time, it works. So waiting for connection after starting for it, so that's good. But then so once you get back a response from the client, we kill the server with the Control C, and then when we start it up again right away, we say connection. Right, this is the client. This is the client saying that we can't connect to it again because it's unable to connect to remote host. The server looks like it's starting correctly the second time, but the client can't get any response from it. Why is that? Remember that the code was written without any error checking. Let's add a little error check into the code and see if we can figure out what is happening. Okay? Why your mom always told you to check for errors. If you add an error check on the line that binds the socket to a port, so right here, if bind blah 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 equals -1, which is the error code that bind returns, we can emit an error saying that we can't bind the port. Then, if we do whatever we just did up here, where we started the server and then killed it and started again right away, it turns out that we can't bind the port because the address is already in use. So, if the server has responded to a client and then gets stopped and restarted, the call to the bind system call fails. But because the original version of the program never checked for errors, the rest of the server code can run. The rest of the server code ran even though it couldn't use the server port. So why is that? Well, bound ports are sticky. When you bind a socket to a port, the operating system will prevent anything else from rebinding it for the next 30 seconds or so. And that includes the program that bound the port in the first place. So the operating system keeps that around, I think, for performance reasons. So like you want to reuse it, but it's like some other thing in your program wants to reuse it again. It I don't know. I think it just quickly can reestablish a connection. See, one of those things where maybe an LLM might help. To get around the problem, you just need to set an option on the socket before you bind it. So int reuse equals 1. So then we call this piece of new code here is called set sock opt with the descriptor to the listening socket. I don't know what sol socket is, and so reuse ADDR means maybe socket reuse address. Maybe this is like a flag to say to reuse. Yeah, this makes the socket reuse the port. So given this listener socket descriptor here, find that socket corresponding to this descriptor and reuse it, or set it to be reusable, I guess. So this code makes the socket reuse the port when it's found. That means you can stop and restart the server and there will be no errors when you bind the port the second time. Okay, let's actually quickly edit our code here to do error checking like this. So I'll just do this. What is it? Int bind result. I'll just do it like this, and then if bind result is equals to -1. Okay, I'll emit an error. Fprintf cd error can't bind the port. I'll just make a new line there, and then I'll exit. Okay, and then where is it? How do we check for this? So when you bind a socket to the port, the operating system, blah, 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 blah. Okay, so we need to set this option before we bind it. So we need to do this before we bind it. So maybe something here. Int reuse equals 1. Actually, let's try to reproduce the problem first before we fix all this. Yeah, let's actually try to reproduce the problem. So we have, how do we say this? So we have the server and we have the client. Ooh, this. Oh yeah, I was trying to do stuff here straight. Okay, so we can do, let's see, gcc main.c, out. Okay, so we'll wait for connection. I think if we just do this and do it again, do this, do it again. Okay, let's telnet. I think we just do that. Okay, so then we can just kill it, go again, can't bind the port. Okay, cool. So a client connection must have been accepted first for this to happen. So now we can't bind the port. So we were able to reproduce that, and given that I've already spoken for more than 30 seconds, if we did this again, it doesn't work. Uh-oh. Did we break something? How about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Wow. Let's see if we... Okay. Maybe that will like kind of reset it. Wow, look at that. Let's see if we can kill something. 8 out. No? Oops. Ooh. Oh, there we go. See? So, wow, that held the port for a very long time. So, that's not ideal. I don't like this. I don't like having to have an unreliable server like that. So, yeah, let's actually add this code in so that we don't ever have that again. And now we know how to test it really well. So, after we change this code, let's actually see if we still get this problem. So, if set sock opt listener d sol socket. So what is this actually? Let's check it out. What does this mean? Sol socket. What does that mean? Let's search for it. Sol socket. What is sol socket used for? Okay. What is the purpose of sol socket? When retrieving a socket option or setting, you specify the option name as well as the level. When level equals sol socket, the item will be searched for in the socket itself. I think we need to actually read what set sock opt actually does. Let's do that. Okay, so sol socket is the second argument in this set sock opt system call. Int level. So what is level? Level is specified to manipulate options at the socket's API level. Level is specified as sole socket. Oh, okay. To manipulate options at any other level, the protocol number of the appropriate protocol controlling the option is supplied. Okay, so manipulate options at the socket. So what exactly level are we going to mess around with? So we want sockets level. Okay, sure. I don't think it's mandatory to really fully understand that, but okay. So that one seems obvious to me. So then we'll have reuse. I don't know why it's gonna be a pointer to a character. Size of int. Some of this stuff is just so mysterious. Equals -1. So basically, if there was an error, we do fprintf std error can't set the reuse option on the socket. And then we'll exit. Okay. So let's try it again. Fprintf. Okay. Okay, so now we're waiting for connection. Telnet. Okay, that looks good. Control C, do it again. Oh, that's way more reliable. Okay. Yeah, that is way more reliable. That's great. Okay, cool. So we are reusing a port. So means here that the code makes the socket reuse the port when it's bound. That means you can stop and restart the server and there will be no errors when you bind the port second time. That's great. So the RECV function, reading from the client. You've learned how to send data to the client, but what about reading from the client? So basically what we've done so far is our client program, Telnet, has been sending just simple like connection requests to our server program here, and all our server program is doing is accepting that connection and just sending back a response directly without even like caring what the client is sending. Now, if we care about what the client is sending, the data that the client is sending to the server here, to basically the server here, then we would actually have to grab that data from a buffer, and that's the receive function. And the receive function here is going to load up all the data into this buffer for this many number of bytes to read, and then it returns us back here the number of bytes that was actually read. Okay, cool. So that's like the basic thing. So when we want to read data, it'll be in here from the client. Okay, so let's read this in more detail. And descriptor is going to be the socket descriptor. Which one? Client or server? Let's see. So if someone types in a line of text into a client and hits return, the receive function stores the text into a character array like this. Who's there? So an array of characters. Basically, this is the buffer. There are a few things to remember. The characters are not terminated with a null terminating character. When someone types text into Telnet, the string always ends with the /r/n. The receive will return the number of characters or -1 if there's an error, or 0 if the client has closed the connection. So that usually means that if you get 0 back from RECV, receive, it means that there's no more data for the server to send, and or sorry, for the client to send. So the client has closed it. Okay. You're not guaranteed to receive all the characters in a single call to receive. Sure. All right. Okay. So the last point is important. You're not guaranteed to receive all the characters in a single call. So if the client sends like 2,000 bytes and you're only reading 1,000 bytes, you've only read the first one. So here's an example. So that's why we have to like repeatedly call this to get the data that we need and fill the buffer, use the buffer, fill the buffer, use the buffer. Okay, so it means that you might have to call receive more than once. So who's there? Maybe we might have to call receive a few times to get all the characters. That means receive can be tricky to use. It's best to wrap receive in a function that stores a simple null terminated string, null meaning the null character, terminated string in an array that it's given. Something like this. So here's a helper function to get everything. All right. So given some socket descriptor and a buffer character array and the length of this buffer, I assume. Yep. What we want to do here is we're going to call receive to get the number of characters read. Okay. And that's going to get filled into this character pointer, which has buffer associated with it. As length is going to be the length of that buffer, the current buffer. And so while the number of characters that we have read by received is more than 0, and we haven't the last index of this buffer that we have is not equal to new line. What we want to do is I guess move the character pointer by C bytes. So that's just to move the the location, and then consume the number of bytes for that length, and then repeatedly do that filling in the buffer. Okay? Sure. So this is assuming that your character buffer is big enough to store all that data. Okay, so we're just going to constantly move this buffer, the pointer ahead of time, loading up that data into the new blank spot. So it's going to be something like this. So let's say you have, let's see. Okay. So your character buffer, let's say C, is like this, or not C, S. Okay, and the first time around, let's say you're starting from here, in the beginning, and then you move up with C times, and then you end up there. So then you fill up everything in here by doing the RECB call. And then what you want to do is you want to take this pointer here. You want to now move it up to here. So now you're right there because C was, the plus equals C is right there. And so on the next call again, you're going to now, what? Okay. You're going to then get the next view C. You're going to fill that up with another call to receive. And you do that repeatedly, moving this S there, and so on. Okay? So, eventually, if C is equals 0, meaning no more characters, then buff 0 is going to be empty string, else replace the last thing with a null character, or null character, and then return basically the number of bytes that have been read. So, like truly from all that data. Wow, that is so complicated. Sure. Okay. I think this is the reason why, we should have these helpers and just like keep them around. Okay. Here are some other functions that are useful when you are writing a server. Do you understand how each one of them works? So this is the error display thing. This is to open a socket for a server, pf-inet, sockstream 0. Okay, and then this is bind to port. So they're just basically turning all of this complexity here into their individual helper functions. And then say here is just basically send some result back to a client. Okay. So I think we should actually refactor our code to kind of implement all of this and then reintegrate it back into here. So let's just do that real quick. So I think we should need this one first because that's going to allow us to read from the client pretty easily. So we do read in and socket. I'm just going to make this a little bit bigger and I can just read it like this. So character buff len. Okay, then we do pointer to character s, buff and slen, len and c. It's going to be recv, socket s, slen 0, and then what is it? This while loop. Yeah, this complicated while loop. So we want to go while we have characters that have been read in by the receive on that initial call to it. And we want to make sure that the last character isn't actually that null terminating, or not null terminating, a new line, I guess. And then here we just move that pointer up that many bytes. Then we subtract basically that many bytes, saying that this is how many we have left. Then we reassign C by trying to receive stuff again into S. Okay, so remember S is going to be filled with that data based off of wherever you have moved the pointer to. Oops, yeah. Okay, and then we have this final if here. That's just going to return, I guess that's an error. Otherwise, else if C equals 0, that means the client has disconnected. Guess that makes sense. And then else, we finish off the data by adding a null terminating character. And I think this is like the good case here most of the time. And then return then. Okay, so that's very complicated for just reading in data. Okay, next one, error. We want to have the error. Okay, so void. I think let's put it all the way up here. Void error. Pointer to character message. F to standard error. String message stir error no. So basically the error corresponding to no, the string version. So we should probably include that, and I think it was just include error error.h error. Let's see, sys error no.h sys error no.h. Okay, and then we'll exit. All right, and then we'll have one to open the listener socket. So int open listener socket. In S, it's going to be socket pf-inet sockstream for TCP. So we've created the socket descriptor corresponding to the listener socket. And then we do if s equals -1. That means we couldn't create the socket. We'll just call error can't open socket. Just give a new line. Oh, it already has a new line. Okay, cool. The error function already prints out a new line there. So that's okay. And then we return S, the descriptor, to the listener socket, the one that will be bound to a port listening. All right, so now we have void bind to port, and that's going to take in the socket descriptor and the port we want to bind to. We can do struct sock addr in name. Name.sin family is going to be pf inet, and then we're going to do name.sin port is going to be import th2ns 30,000. The name.sin addr.saddr is going to be h2nl addr any. Okay, and then we're gonna do that reuse thing before we actually bind. So it did the reuse thing, and then it attempted to bound. So we can do int reuse equals 1 if set sock opt socket sol socket so reuse addr pointer to a character cast. This reuse size of int check to see if it is -1. Well, if that is, then we still can't set the reuse option. Reuse option on the socket. Okay, but if we can bind, or we can make it reusable, we can now bind. So int c equals bind socket struct sock addr pointer cast. Get the address of the sock addr in and cast that. Okay, size of name. If c is -1, means we couldn't bind to any. We can't bind the port to the socket. Vice versa. Can't bind to socket. Okay, that's done. Now it's this one, int say, and that's just sending data. Yeah, sending data back to the client. So a response. So we'll do int say, int socket, and remember the socket may not necessarily be the listener socket. In this case, this socket corresponds to, if we look at the send here, connectee, so that's going to be the client socket, the socket corresponding connected to client directly. Okay, so pointer to character s, then we'll say int result is going to be send socket s sterlen s 0 if result is -1, meaning that we can send fprintf. I wonder why it's fprintf and not error. Don't call error if there's a problem. You won't want to start the server. Oh, we don't want to exit. That's right. We want to just keep going. Okay, because if we call error, that would exit our server, and then our server dies. So we don't want to do that. We want to keep it running. So that would be error talking to the client, and we're going to stir error no. Okay, then we're gonna return results, which is just then I don't know what, I forgot what send does, but what does send return back again? Oh, we let's see, returns the number of bytes sent or -1. Okay, cool. Okay, so now let's try them out. Do we have everything we need? We need signal, I guess. So, boom, signal. Oops, boom. Include signal.h. SCIO, stdlib, string h, no. syssocket, ARPA iNet, UniSTD, Signal H. Sure. I didn't know it was just no. Okay. So, oh, we need this too? Okay. Let's do that too. Void handle shutdown. Let's do it down here. Void handle shutdown int sig if listener D, meaning that if we have a socket, we want to close the socket. So listener D, we have a listener socket, that is. Then we're going to do fprintf cd error by exit 0. So exit cleanly, and this we need to declare. I think we'll declare all the way up here. So this will be the global listener socket. It's in the global level outside of main. Okay, std steady error. Okay, great. So now, okay, main function. So we got to rewrite a lot of this. So now it's over to you to write the main function. You'll need to create a new server socket and store it in listener D. The socket will be bound to port 30,000 and the queue depth should be set to 10. Once that's done, you need to write the code that works like this. Okay, so accept the connection from the client, send knock knock, then check that they say who's there. So try to receive a who's there. Okay, say Oscar. So I send back Oscar. Check that they say Oscar who. Say Oscar silly question. You get a silly answer. Okay, try to check the error codes, and if the user says the wrong thing, just send an error message, close the connection, and then wait for another client. Good luck. Whew. Okay, let's do it. All right, so here, I don't think we need any of this anymore. This is all like already built, or we've already started, working on that. So it's going to be int, or listener D is already defined, so we just need to set it. I think it's just going to be calling open listener socket because we get back a socket descriptor here, and this code looks similar to what we had before, so I'm going to do that. So if I go back down, I'm going to say open listener socket. Simple as that. Next, we need to bind. So we bind the socket with bind to port with our socket descriptor and our port. I don't know why we have port here, but yet this is hard coded. Let's see. I think that's a bug. I think we should just do port like this. Yeah, because it's the only time we use it. So let's just do it like that. So bind the port with the listener D and then the custom port. And then this already checks to see if we can reuse the socket and set it to be able to reuse. This will just bind with all this necessary information in the struct. Okay, so let's do that. So we're gonna bind. We'll say bind to port listener D. So that's our socket descriptor and our port 30,000. Okay. So now we listen. So blab. We're like blabbing now. So listen here with queue depth of 10. We put, okay. So we can just comment. Here's the B part of it. Here's the L part of it. And now we have this piece of code here where we want to start listening. So here's the accept. Right here is going to be A. And we don't want to receive the data right away. We want to, we don't want to send data right away. We want to receive. So, okay, so this is going to be the tricky bit here. Say knock knock. So we'll say knock knock. We'll send knock knock. So I think that's calling what? Say here. So let's clean this up. So we're gonna say our character. Okay, so say knock knock. So say with the client socket connect D because that's coming in. We accepted that connection from the client. So we're gonna use this socket descriptor to say knock knock. Knock knock. Okay. So at some point then the client gets that. And then we're gonna check that they say who's there. So that I think it's just read in. We have this read in thing here that takes in a buffer. So we'll need to allocate some buffer. Let's see, to character buffer. I don't know, 128 characters. Let's just say that. So read in. The socket is going to be, I guess, connect D. And then buffer is going to just be buffer. Length is 128. Okay, let's actually make this a variable. Int buffer size 128. We'll say buffer size. And then we'll say buffer size here. Okay. So we'll read in data into buffer. And then so check that they say who's there. So we're gonna have to do like a stir comp maybe. So let's include string. Do we include a string? We have string, yes. Okay, so let's do stir comp. So if stir comp buffer is who's there, okay, what do? We say Oscar. So we say connect D. So we use say to send Oscar. Okay. And then check that they say Oscar who. So we read in again. So in this case, we could reuse the buffer, I guess. Read in, connect D, buffer, buffer size. And then we'll say, check that they say Oscar who. If stir comp buffer Oscar who, then say Oscar silly question, you get a silly answer. Okay, so we can say connect D. Oops. Say connect D. Oscar silly question, you get a silly answer. Ooh, I hope that fits. All right. So now we don't need that. We don't need this, and then we close the connection. So we don't need this anymore either. Okay. So does this fulfill the requirements? Well, let's say this. It says this. Looking at. Okay. You'll need to create a socket. Okay. Try to check error codes, and if the user says the wrong thing, just send an error message. So the else here is going to just do send an error message. So say connect D error, and then close the connection. So I'm going to say close connect D. And then right here, they're gonna want to read in and say something too. So I can say else say connect D error, and then close connect D. Okay. And then here by default, if it gets down here, we'll just close the connection. So this is BLA. What's the other B? I think buffer. Anyway. Okay. So ooh, that's a big one. And connect D. Also, we do need an error handle. Okay, so let's do this. This one can be nothing. Okay, so we can just say if connect D is equals -1. We can say error. Oh, we don't. We should just close the connection. So we had to just do. No, we don't need to close. What do we need to do here? We just close it? We just exit the program? It says can't open secondary socket, I guess. Can't open client socket. Let's do that. So that exits. Okay. I think this is similar. Do we always have to put RN? Okay, let's do that. Supposedly you need to. I think this is just for like telnet stuff. Yeah, I think this. Oh no! This is for. Yeah, this is like for telnet. Okay. Read and. Where's knock knock? Oh, knock knock. RN. Then we want who's there. Okay, and then you should say who's there. You should say who's there. Oh, that's the error message right here. Okay. So if there is something, but oh, so we need to check for 0 because that's their if it matches. We want to say Oscar. So if it matches again. Okay. Otherwise, we'll just say error. Okay. Should we just say error or should say you should say who's Oscar? You should say Oscar. Okay. And we do that. And then if there's an error here, you should say Oscar who RN. And then this one should say RN too. Every time we send, we need to send this carriage return. I think that's like that's probably like a telnet thing. Okay. And then this will actually flow down and close. Okay, so we don't need that. Just reviewing my own code. Okay. So let's actually just test it. Let's just test it. So okay, waiting for connection. If I do telnet, it says knock knock. And then if I do what's it? Who's there? You should say Oscar. Wait. Who says who's there? Do I say who's there? Yeah, who's there? But it says you should say Oscar. Why? Wait, so this part is Oscar. Oh, my whole flow is wrong. Wait, who's there? You should say who's there. And this one should say, we should check Oscar here. Wait, who's there? And then I say Oscar. Then you should say Oscar. Okay. But why am I closing right away? It says you should say Oscar. Oh, let's try it again. I'm confused. Oops, I should compile. Okay. Okay, knock knock. Who's there? You should say who's there. Why is this not working? If stir comp buffer, who's there? Is it because I'm not stripping out the /r/n? Maybe that's the reason why they do stir n comp instead. They want to compare the first character. So maybe that's the reason why. So that means we should do this one too. Maybe they want to avoid the /r/n stuff. That's the reason why, most likely. Who's there? Ah, Oscar. Oscar. Who? Oscar, silly question. You get a silly answer. Okay. Ooh, that's tricky. This can get very hard, confusing to understand, especially this read in one here. Ah, but yeah, it's just practice, I guess. And notice that it's still in a while loop. So really, even though I am disconnected as a client, the server is still running. So I can actually just ask for another joke. Who's there? Oscar? Oscar who? And I just do it again. So yeah, I think it's actually exit. Ugh, yeah. So anyway, continuing on. Now that you've written the knock knock server, it's time to compile it and fire it up. So basically this. The server can tell you a joke, but what happens if you break the protocol and send back an invalid response? You should say who's there. Connection closed. Okay. The server is able to validate the data you send it and close the connection immediately. Once you're done running the server, you can switch back to the server window and hit Control-C to close it down neatly. It even sends you a farewell message. Bye. That's great. The server does everything you need it to do. Or does it? Oh, let me actually kill the server, see if we get the bye too, because we had a signal handler and we didn't. So that's interesting. This is supposed to have that signal handle shut down. Oh, we didn't register the SIGINT. Let's see, did we have SIGINT registered? Right here, catch signal. Oh, we never implemented it. Oh, it's okay, whatever. Yeah. The server can only talk to one person at a time. There's a problem with the current server code. Imagine someone connects to it and he is a little slow with his responses. Then if someone else tries to get to the server, she can't. It's busy with the first guy. That's true. The problem is that the server is still busy talking to the first guy. The main server socket will keep the client waiting until the server calls the accept system call again. But because of the guy already connected, it will be some time before that happens. So this can only handle one connection at a time because it's in this while loop here. It'll accept, and then it'll just wait for the next one. Like the next one's in the queue. Okay, yeah, that makes sense. So when we accept the client connection, even if we're waiting right here, this read in here for some sort of response from that current client, it's just going to perpetually sit there, and all the other clients that are queued is just going to be waiting for it. So let's actually just test that out. So here I have one. Okay, and then I'm going to have another one. I'm going to create another connection. So I'm going to do Control-C. Create the connection, the first connection. Control-B-C to create a new tmux one. Then let's just do telnet again. Just create a new connection. Just create a new connection to the server. Okay, so notice how I haven't gotten anything back because my server is still handling this current connection here. So if I do Oscar, oh wait, actually who's there? Okay, still this connection is still in the queue. Oscar who? Oscar, silly question, you get a silly answer. Okay, now what happens? There we go, knock knock. So now this loop executes. So basically, once I close that first connection by telling the full joke, the next iteration occurs in this loop and handles the next client coming in. So it's kind of inefficient, right? We want to be able to handle multiple connections at once. So how do we do that? Okay. Well, you can fork a process for each client. When the clients connect to the server, they start to have a conversation on a separate newly created socket. That means the main server socket is free to go to find another client. So let's do that. When the client connects, you can fork a separate child process to deal with the conversation between the server and the client. So we could just fork that part of code that handles all the client stuff. And that frees up the parent process to continue handling other clients. And by handling other clients, it means it forks those clients too. Handle the next one, forks, handle the next one, forks. So it's never like just stalled waiting for the client. Okay, so while the client is talking to the child process, the server's parent process can go connect to the next client. Great. So the parent and child use different sockets. One thing to bear in mind is that the parent server process will only need to use the main listener socket. So basically the listener D socket. That is because the main listener socket is the one that is used to accept the new connections. On the other hand, the child process will only ever need to deal with a secondary socket that gets created by the accept call. So the child one only needs to use this one here. That means once the parent has forked the child, the parent can close the secondary socket and the child can close the main listener socket. So once we fork, the child will just close this one, and after forking, the parent can close this one, because this one will actually be opened on the child one, and the child never needs to listen for anything. So it doesn't need to share that either, so we can just close it on that side. Okay. Okay, continuing on. All right, so this is a version of the server code that has been changed to fork a child process to talk to each client, except it's not quite finished. See if you can figure out the missing pieces of code. So basically, what do we do here? This is what? If fork or PID. This will probably be like we probably fork when we accept, and we close. This is the child process, right? So like if PID is 0, right? If the PID here is 0, we'll just close the listener socket, and then we do all this here, and basically on the outside of the if condition, we'll close the child socket right there, right away. Okay. Oh, not the phone. Alright, let's parse this again. So for sure we fork here, and if it's a 0, we're gonna just handle the child here, because this is where the child process executes. Child process will execute everything in here because that's the new process we created with fork. And here is where the parent will continue to execute. So I am thinking here that connect D. Okay, so as soon as we get a child or a client socket, we can do int PID fork. If not PID, meaning that's child. What we want to do is close the listener D socket immediately. And then all of this here, so all of this here will be for the child. Okay. And then right out of here, we just close connect D right away. At least the parent's version of it. So this is the parent version of connect D. Okay, maybe. And this one's close connect D. What should the child do when the conversation is done? What should a child do when the conversation is done? That's interesting. What should it do? Do we allocate any memory in here? No. should we... I'm stumped. I know... Yeah, I don't know. Let's see, what should the child do? So fork. So if not paid, so not fork. That's correct. Close listener D. Exit 0. Oh, we should exit itself. Oh, okay. So, okay, once the conversation is over, the child can close the socket to the client. Once the child process has finished talking, it should exit. That will prevent it from falling into the main server loop. Because if I don't exit, it's going to stay in this while loop and run forever. And I'm going to run out of memory if I keep spawning more child processes because these guys just never exit. Okay, cool. So let's try it again. Let's do the same test case. Let's have these two here, two clients. Then we'll have this server. Compile, we'll listen. And if we did this, we get knock knock. We should get knock knock right away here too. Yeah. Wow. Okay. So let's do this. Let's do Control B, C, get to B top. And how many A.outs do we have? We have 3 A.outs. So this one here is going to, oops. Okay, so this one here is our server. These two here are our client threads that our server has spawned 384 kilobytes of memory. All right, so I'm thinking that if we did telnet 127.0.0.1 30,000 again, we'll get a third one right there. 384 kilobytes there too. So we can do who's there, Oscar who. Okay, so now that exits, that thread exits, that child process exits. So now at some point, if we did A.out again, this uses 0 memory, and I think it takes some time for it to like kind of go away. But let's see what happens here. Who's there? Oscar who? Okay, that closes. Okay, that's 0 memory now. And then Oscar who's there? Oscar who? Okay, so all that is 0 now. So what is the state of these processes? I don't even know. Huh. So A.out. They're using nothing. I don't know if like this actually shows us the state of these processes, but I guess if I just exit like this, all of a sudden, weird. Yeah, but if it's using 0 memory, then that means it's not there anymore. So I guess that. Oh yeah, because it's process tree. Oh, okay, yeah. All right, whatever. So let's try to modify version of the server. You can compile it and run it in the same way. If you open a separate console and start Telnet, you can connect just like you did before. Everything seems the same, but if you leave the client running with the joke half told, you should be able to see what's changed. Okay. If you open third console, you will see that there are now 2 processes for the server, one for the parent and one for the client. Great, that's what we saw. This means you can connect even while the first client is still talking to the server. Now that you've built an internet server, let's go look at what it takes to build a client by writing something that can read from the web. Ooh, interesting. Okay. Writing a web client. What if you want to write your own client program? So basically, we're not writing a server anymore. We're writing a client. So we're doing the other side. We're programmatically making a client program out of sockets. And it's going to be HTTP. So HTTP is a lot like the Internet Knock Protocol you coded earlier. Okay, all protocols are structured conversations. Every time a web client and server talk, they say the same kind of things. Open Telnet and see how to download this thing here. Okay, so just how we do this? Do we just open Telnet and just do that? Okay, let's do it. Quit. Okay. Telnet. I know Wikipedia is still around. Okay. Now what do we do? Is this connection closed? Is it just Telnet and slash wiki slash O'Reilly? Oh, is that it? Oh, I see. We were supposed to issue a GET request. Okay, there's no way I can issue a GET request that fast. So I had to do like GET like that. There's no way I can go that fast. Okay, so let's just do it like this. Let's copy and paste real fast. So if we were to do GET wiki O'Reilly media HTTP 1.1, and we'll say host wikipedia.org. Okay, we did this. Let's just, oh, we had to give new lines like this. Okay. Copy. Let's go fast. So we did that. B. Almost. Oh, moved early. We did get something. Okay, cool. So it moved to where? Oh, I guess it's now using HTTPS. Yeah, I think it's using like HTTPS now. So this is just too old. Okay. So when your program connects, so it's supposed to come out with HTML basically. When the program connects to the web server, it will need to send at least 3 things: a GET command, host name, and a blank line. So this is what a basic HTTP request looks like for a GET request. Okay. Okay. So, but before you can send any data at all to the server, you need to make a connection from the client. How do you do that? Okay, so this is how we're going to make a client that will do this. But I guess this is a bad example because we need to do an HTTPS now. We'll find something else. Okay, so blab again. Oh, begin talking. That was what it stood for. Okay, so clients and servers communicate using sockets, but the way that each get hold of a socket is a little different. You've already seen that servers use the blab sequence. Okay, a server spends most of his life waiting for a fresh connection from a client. Until a client connects, a server can't really do anything. Clients don't have that problem. A client can connect and start talking to a server whenever it likes. This is the sequence for a client. Connect to a remote port, begin talking. So remote ports and IP addresses. When a server connects to the network, it just has to decide which port it's going to use. But clients need to know a little more. They need to know the port of the remote server, but they also need to know the IP address of the server. Okay? Internet addresses are kind of hard to remember, which is why most of the time human beings use domain names. A domain name is just an easier to remember piece of text like O'Reilly.com. Even though human beings prefer domain names, the actual packets of information that flow across the network only use a numeric IP addresses. So this is just like an alias to an IP address. Right? So your domain name, your host name, underneath the hood, it's just an IP address. And we actually get the IP address using something called DNS. So create a socket for an IP address. Once your client knows the address and port number of the server, it can create a client socket. Client socket and server sockets are created the same way. So same thing. This is going to be the client socket. So it's just like a descriptor. It's like a placeholder. It's not until you have to bind. And I've noticed that it's only when you bind, it's how you actually kind of indicate what kind of socket it is for. So yeah, the difference between client and server code is what they do with sockets once they're created. Yeah, so creating a socket, at this point, you can't tell whether or not it's going to be like a listening, like a server socket or a client socket. You just like kind of allocate a resource. You're telling the OS, hey, give me a resource to a socket, like a pointer to a socket. So then what you have to do is kind of make it useful with like the stuff that you do after it. So in this case, let's see, the client will connect to the socket to a remote port. So this is how we actually create that. So we do struct sock EDDR in SI, memset, okay, do memset 0, we zero it out. Okay, so what's memset? Memset. So the memset function fills in the first n bytes of the memory area pointed to by S with the constant byte C. So this is memory location S, the byte we want to fill it with, and how many bytes we want to fill up. So we're going to fill up pretty much the entire SI struct with zeros, starting at this memory address, which is basically the beginning of the SI struct. Then we're going to assign all these properties here as usual, but the different thing here is that we're going to have to specify the server's IP address using this inet ADDR function call. Okay, then we just do connect with this call here, and then what? Huh. Oh, wait, hello. I don't want to know how to connect a socket to an IP address. I'm actually human. I want to connect to a real domain name. So the above code only works for numeric IP addresses. To connect a socket to a remote domain name, you'll need a function called getAddrinfo. So I'm guessing they're going to modify it. Yeah, right there. Okay, cool. So getAddrinfo gets addresses for domains. The domain name system is a huge address book, so DNS. It's a way of converting a domain name like www.o'reilly.com into the kinds of numeric IP addresses that computers need to address the packets of information they send across the network. Create a socket for a domain name. Most of the time, you'll want your client code to use the DNS system to create sockets. That way, your users won't have to look up the IP addresses themselves. To use DNS, you need to construct your client sockets in a slightly different way. So we need to include this new header here, netdb.h. Okay, and then we just call this. I guess we need also two structs now. Hints is the one that has that DNS IP information. Okay, so the getAddrinfo constructs a new data structure on the heap called a naming resource. The naming resource represents a port on a server with a given domain name. Hidden away inside the naming resource is the IP address that the computer will need. Sometimes very large domains can have several IP addresses, but the code here will simply pick one of them. You can then use the naming resource to create a socket. Sure. So once all that's done, then we can really create a socket. Okay. Finally, you can connect to the remote socket. So, okay, all that just to resolve a domain name to an IP. All right. Okay, so the res here is going to be our usual one that we would specify here equivalently. All right. Okay, finally connect remote socket because the naming resource is created on the heap. So it's created on the heap. You'll need to tidy it away with a function called freeAddrinfo, which is like a specialized version to kind of free up that struct, the stuff inside that struct. It's a helper. It probably internally calls free. Once you've connected a socket to a remote port, you can read and write to it using the same recv and send functions you used for the server. That means you have enough information to now write a web client. Whoa! Okay, how much do we have left? Oh, we have quite a bit left. Okay, so let's pause here and let's write the web client next time. Thank you.